Well, hello everyone. Open Zoom meeting. Join a meeting. What am I supposed to do here? Meeting topic. Start video. Okay. There we go. Recording, that's good. Yeah, that's good. Tuesday, August 18th. Physics 2. I wonder if I have any students showing up here for this. Not yet. Nobody has showed up yet. Well, even if nobody shows up, I'll go ahead and have my class. Right now, it's just me, though. Gee. That's not good. Tonight, we're supposed to study see who that is. My phone. Hi. Well, it's 5:25, and I've logged on here, but right now I don't have any students. Oh, waiting room. I wonder how I get to a waiting room. Yeah, I did earlier. It says recording. It does say recording up in the corner. That's good. Let me read this down here. It says participants, chat, share screen, something about, I can't read it. They write too dang small for me. I don't know what that says. Don't see anything about a waiting room, though. It did say that earlier. Yeah, I'm hoping they will log in because I'll feel a lot more comfortable if I have some students. It's so boring to just blab into empty space. Maybe you could, are you where you could see if I'm connected? And by the way, I filled in all of those things that you told me to in physics and in dynamics. in the units 1, 2, 3, and 4. You want the T10? Yeah, that's what I was thinking. Yeah, maybe not a good idea. I could text you, I guess, but you're okay. All right. Well, I still don't have any. It says invite. It says mute all, unmute. Yeah, it said the meeting 5:30 and it connected. And it's got me on there, participants, but I'm the only one, which is kind of weird. Usually there's a few others. Hey, wait a minute. I just got a customer. Daniel Ickner. Welcome, Daniel. Unmute and say hi, Daniel. I think we're in business. I've got one student that just logged in. Well, he just logged in and then he disappeared. He's not on there now. Let's just be patient, I guess. It says oh, wait a minute. Hey, wait a minute. I got another one. I've got, something about a waiting room? No, I don't see anything about a waiting room. I do see Daniel Ickner, though. He's logged on. Hey, Daniel.
Hello.
No, I didn't see that. Let's see. Okay. I'm looking at the bottom and it says security, participants, chat, share screen, and something about pause, stop, recording, and reactions. There's nothing about a waiting room. Hey, wait a minute. I just got another customer. Zach. I've got a customer. Zach. Yeah, but how do I get him out of the waiting room? When I click what? Oh, okay. Well, when I click participants, it says well, it lists these myself and Daniel and Zach is what it has. It doesn't say anything about a waiting room. Well, they're not responding. Hey, oh, there's another one. There's Chastity. Chastity, Daniel, and Zach. I've got 3 students. One of you guys, do I need a phone? Is that what you're saying? I don't know. I don't know if I'm muted. I hope not. How do I find that out?
I can hear you.
Hey, you
Yeah,
can
you're not muted.
I'm not muted, and I'm picking up students, John Gilliam, Zach, Daniel, Chastity. Hey, I'm glad that we got some customers here. I've got 4 students already. I think maybe they're slowly coming on. Yeah, they seem to hear me okay. Now tell me your name. Yeah, tell me your name.
Well, my name's John Gilliam.
Okay, John. Yeah, that's John.
My name is Chastity.
Hey, hello, Chastity. Okay, bye-bye for now. All right. Well, we're finally connected. I'm your instructor, and we're going to have a wonderful online Physics 2 class. And let me see how many people I have right now. Okay, what I've got right now is, well, quite a few wonderful students. I've got Jacob, Daniel, John, and Chastity, and Zach. So we're going to go ahead with our Physics 2 class. Now on Blackboard, there's a syllabus, and I want to know if you guys have access to that syllabus. And on Blackboard, there's a class schedule. How about it?
Yes.
Do you have access to that?
Yes.
Good, I heard a yes. Somebody else say yes.
Oh yeah, I've got it printed off right in front of me.
That's a good idea. Print it off. You've got the syllabus. Just a minute. I got my IT person online here. Let me see what she says. Yeah, hi. I need to pin myself. Yeah, it's a little bit crooked. You're right. I don't know how I can fix that. Scoot it back a little bit. Oh, okay, hang on. And now point it down just a little bit. How's that? A little bit better. Well, I've got quite a class there, and I'm ready to go. Thank you. Bye-bye. That was my IT person, my 30-year-old daughter, my youngest. My oldest daughter is, oh gosh. She was born in 1969. Yeah, I think that's right. She would be, yeah, she's 51. Yeah, my oldest daughter's 51. That makes me feel old. Okay, well, we're going to go ahead with our class. Now, you guys have access to the syllabus. And in that syllabus, it tells you about the book. Now, I happen to have a copy of the book, a hard copy. But you can just get a electronic book. This is what mine looks like. Of course, yours might not have Pistol Pete on yours there. But this book, the price is right. It's free. It's what they call what do they call it? Stacks something. You know what I'm talking about?
Yeah, it's the OpenStax.
OpenStax, that's what they call it. Yeah.
It's like Rice College does it. They do a bunch of them.
Yeah, it's OpenStax, and it's free. And in the syllabus, it tells you how to obtain the book free. Well, what you'll get is a electronic book. And let me ask you guys, have any of you obtained the electronic book?
Yes.
I have, yeah. I got it today.
Great. You know what I did is I took a thumb drive and I copied my book from the OpenStax to my thumb drive. Did anybody do that? Nobody answered me on that one. Unmute. If you have copied the book on a thumb drive, then tell me. If not, that's fine. But I was amazed. That book was copied onto my thumb drive. I don't know, count to 5, pretty slow, and that was it. This entire book is on my thumb drive, and I'm sure you can do the same thing. Okay, well, what else is on the syllabus that you need to know about? Let me look and see here. Let me see if I can find my syllabus. Yeah, here it is. Well, we're supposed to study chapter 5 for the next tonight and also next Tuesday night. See, we only meet for the lecture on Tuesday nights. And then on Thursday nights, we're going to be on campus. And we're going to do our experiments. That's all we're going to do on Thursday night is our experiments. Now, I put the first experiment in content on Blackboard. So if you'll go to content on your Blackboard, the name of that first experiment is electrical measurements. And it is on Blackboard. And it's under content. You go to content. And you'll find the first experiment. You can make a copy of it. I've made some copies, and if you forget your copy, I can give you one in the lab. The lab is all this is on the syllabus. You could read it, but I'll tell you where it is. It's AB 276. Go upstairs at the Northeast campus. It's on the northwest corner upstairs. It's right next to the bathrooms. And it's 5:30 to 8:20 on Thursday. And the lab we're going to do then is electrical measurements. Read that lab. I put it on content so that you can read it. And I'll show you what I want you to do on Thursday. So that's your first lab. Each lab is going to be worth 10 points. And you'll have a total of 100 possible.
Sir, can I ask you a question about this week's lab?
Please do.
At the end of July, I had COVID, and I'm recovered now, and I've been in touch with Matt Sharp. I sent you an email about this, but he wanted to just add a little extra time for the, I guess the, what's that federal organization, you know?
CDC.
Yeah, so I'm well over the CDC guideline, and I'm definitely over it, but he wanted to give it another week just as a precaution. So I'm not technically allowed on campus until the 24th. but I have some friends that are taking this class. Would it be possible for me to print the lab off and get data from them and still get credit?
Now, tell me your name.
John Gilliam.
Okay, John. In the syllabus, it says we have 10 labs, but I'm going to have a makeup lab. I think we got time to do a makeup lab, John. And
Okay.
so just skip this first lab and then do a makeup lab. But I want you to study it because you'll need to know this stuff.
Oh, no, I'll definitely read it and study it and prepare. I didn't want to get penalized for following the TCC guideline. So
Right. And when you do come, and this is for everybody else, including myself, we're going to wear masks. Now, you won't be able to understand me if I'm wearing a mask, but if I stay far enough away from you guys, I think I can take my mask off to explain how to do the experiment, and then I'll put it back on. So that's my plan. And you guys need to keep wearing masks until we hear otherwise. But thank you for telling me about that, John. I'll make a note of that, and we'll work through that okay. Is there any other person that wants to make a comment about the syllabus or the schedule or the lab or the book?
In the past, for chemistry and other labs, there was like a document we had to sign, like a liability thing for the school. I am not seeing that. Maybe I'm just missing it. Is there one of those we need to sign?
Yeah, I think what you're talking about is a lab, a student lab agreement that you're supposed to fill out so that for safety purposes. Is that what you're talking about?
Yes, sir. That's exactly it.
Yeah, it's this. I forget the name of it, but it's something that I've forgotten about. But I'll get that. I'll do that. The student lab agreement. Basically, it's just to be careful because in this particular lab, we will be dealing with voltages and currents. And if you're foolish, you could get hurt. But I'm going to try my best to prevent that from happening. But thank you for reminding me about that.
No problem. And do you have a dress?
We'll put that on the blackboard. Now, anybody else a comment or question on anything dealing with the course, the syllabus, the schedule, the book, where the lab is? It's in the northwest corner of the Northeast campus. Well, okay. I think what we're going to do is start on our lecture here. We Tuesdays we meet for basically 3 hours. We'll take a little break in the middle, but we're going to meet on Tuesdays from 5:30 to 8:20. So that's a long time. But we'll only meet once a week for the lecture. And the topic basically right now is Coulomb's law. So let's get started. I'm going to erase this and we're going to talk about Coulomb's law. Now Coulomb's law, if you want to know what it says, this is what it says. that's it. It's really the basis for our course. You know, different courses have the most important equation. Like, for instance, in Physics 1, the most important equation was Newton's second law, F equals ma. Anybody remember F equals ma from Physics 1? I hope so.
Oh yeah.
That's probably, I would say, number one. And every course is like that. I don't know what you'd say algebra was. Maybe the quadratic formula, for instance. Maybe, I don't know. Fluid mechanics, the most important equation was probably Bernoulli's equation. But in this class, this is Coulomb's law. It's the most important, and it deals with charges. It turns out that matter has mass and matter has charges. And I'm sure you're familiar from chemistry that you have protons and electrons and neutrons. They all have mass. In fact, I've scribbled down some of those things. The mass of an electron is very tiny. It's 9.1094 times 10 to the minus 31 kilograms. So it's very tiny, but a proton is much heavier. It is 1.6726 times 10 to the minus 27. So it's much heavier. Let me just see. I'm curious what the ratio would be there. It looks like maybe a couple of thousand. Let's see. 1.6726 e to the minus 27 divided by 9.1094 e to the minus 31. Yeah, you know what? It's 1,836 times as massive as the electron. So the proton is much, I guess, heavier, you might say. It's got more mass anyway. 1,836 times the mass of the electron. But the thing is that the charge is the same. It's just that the electron has a negative charge and the proton has a positive charge. They're equal. Now the unit they use for charges are coulombs, in honor of Coulomb's law there. It turns out that these both have a charge of 1.602 times 10 to the minus 19 coulombs. I put units in brackets often. So, and the rule is like charges repel and unlike charges attract. A lot of this stuff you know from chemistry, or if you read your chapter, we're in chapter 5 actually. You know that like charges attract. If you have like charges, no. I did that wrong. Like charges repel, and unlike charges attract. And I ran out of space there. I'll write it up here. Unlike charges, they attract. Did I say that right? So if you had a positive and a negative charge, they attract one another. This is a little different than gravity. There's an equation for gravity very similar to this. Let me write that for you. It's Newton's law of Newton's universal law of gravity. Let me write that for you, and we'll talk about gravity for a minute. I'm talking to you about gravity because the equation is so similar, only it's not charges, it's masses. These r's here are the distances between the masses, and that r squared there is the difference distance between the charges. But gravity, as far as I know, always attracts. Now there is some interest in anti-gravity, and if any of you guys can figure out what that is, you'll be famous, because that would be pretty neat if you could find masses that repel each other, sort of the opposite of gravity. This is called Newton's universal law, universal constant. And I was going to tell you what that is. Let's see. I wonder if I have that written down. Uh-oh. I might not have that written down. Well, we could always go to the index. Let me look. Let me see if I can find that. Or some of you guys that have a Google it for me while I try to find it here. The gravitational constant. Okay. I don't see it in the index. Dang, I was going to show you that. Okay, let me keep looking. I'm not quite ready to give up on that. Yeah, here it is. This is called Newton's gravitational constant. Notice it's very, very tiny. I mean, 10 to the minus 11. Now this K here, that's called Coulomb's constant. This is Newton's gravitational constant, but that K there is called Coulomb's constant. And it's equal to now it's a very big number. I mean, that's 8.99 10 to the 19th. That is a humongous number. How many zeros is that? No, that's wrong. It's just 9. 8.99 times 10 to the 9th. Now let's make sure I'm not lying to you. Look in chapter 5, and let's look up Newton's constant there. I'm sorry, Coulomb's Coulomb's constant. I'm looking for it. Okay. Yeah, there it is. I got that right. Yeah, 8.99 times 10 to the 9th. There it is. The gravitational constant is very tiny. Coulomb's constant is very big. But it seems that we're more influenced by gravity. I don't know if you've ever slipped and fallen down, maybe on roller skates or a banana peel. And when you hit the ground with a thud, it's kind of uncomfortable. Gravity plays a big role in our life. The reason why it seems so powerful is that one of these masses is the mass of the Earth. And the mass of the Earth is quite large. I could give you that also, but we don't need it right now. The other mass would be you or me, if you want to figure the force of gravity on you. But that'd be kind of fun to do. Let me see if I could do that. The mass of the Earth. Let's see. Do we have that someplace? Dig around a little bit here. Yeah, I can't find it. We could always look it up. The mass of the Earth. Yeah, I think I found it here. This is probably right. Yeah. Okay. Can you see that? That's getting kind of low, but I think you can see it. What I have written down in my notes is the mass of the Earth is 5.97 times 10 to the 24th kilograms. Pretty big. Okay. Well, let's figure the force of gravity on you or me. All right. All right. Well, let's do that. That'd be kind of fun. We're really trying to understand Coulomb's law, but see, these laws are so similar. They're both what they call inverse square laws. See, if you double this distance between the bodies, 2 squared is 4, so you have 1/4 the force. Same with gravity. If you double this distance here, the force of gravity is 1/4. Now, here in this case, you'd have to take the distance from the center of the Earth to where you are. Well, to do that, we'd need the radius of the Earth, which I think I have that too. Well, I would like to continue on and talk to you more about this law of gravitation, but that's really not what we want to study. We want to study Coulomb's law. So let me just say goodbye to the law of gravitation for now. But let me just add that this constant is so big. How come Coulomb's doesn't have a bigger effect on us than gravity? Gravity is the constant so small. The reason is that these charges are generally small because what they are is the unbalanced charges. See, matter, we have equal number of electrons and protons. And so what this would be an unbalanced charge. If you have more protons than electrons, that would be a positive charge. If you have more electrons than protons, this would be a negative charge. If the numbers are the same, you don't have any net charge. That's a net charge. That's how come that doesn't seem to affect us that much until you put your finger in a wall socket, and then you'll discover it has quite a large effect. Okay, well, instead of spending a lot of time on the law of gravitation, I'm just going to skip that and go on and talk about Coulomb's law. And we'll work some problems. Now, when Coulomb wrote his law, this is the way he wrote his constant. But since then, they have changed the way they express that constant, and they write it like this. Hope you can read my writing. That's supposed to be a pi. It turns out that this right here is a more fundamental constant. You know, there are just a small handful of fundamental constants. The speed of light, for instance, is a fundamental constant. This thing here is, it's got a fancy name. It's called the permittivity. See if I can spell it right. It's called permittivity, and it can operate in a vacuum, which is pretty amazing. See, these forces between charges, you don't need anything in between them. You can be out in outer space and just have nothing, but they will still attract or repel. And this is equal to now, I did that backwards. Don't write that down. I did that wrong. There, I think I have it right now. It's called permittivity. Now, that's the permittivity of a vacuum. You'll find that Coulomb's law can operate in substances like wood or water or air or 100,000 other things, okay? Plastic or whatever. But let's just do this and see what happens and see what we get for our value of Coulomb's constant. I want you to take 1 over 4 pi 8.854. Is this showing up? Yeah, barely. Yeah, it's showing up. 8.854, 10 to the minus 12. And put that in your calculator. I'm going to be quiet for about a minute or so. Everyone in my class needs a calculator. And I think we can learn better if we all participate. So I'm going to be quiet. And I want you to put that in your calculator. And I'm going to do the same. Let's see what we get. Go for it.
I don't know if I'm seeing it right on the board, but I got like a ridiculously large number.
Yeah, it is a ridiculously large number.
Okay. Okay, cool.
I got 8.99 times 10 to the 9th. How about you?
Yeah, that's exactly what I got.
Well, you know what? That's what Coulomb's constant is, 8.99 times 10 to the 9th. Now these units here are Coulomb squared divided by Newton meter squared, but it's in the denominator. So what you get is Newton meter squared per Coulomb squared. So what I'm showing you is, hey, that worked pretty good. It can also work the other way. You can take epsilon sub 0. That's a little Greek letter epsilon. See, the capital Greek letter is, it's like our English E, but did you know the Greeks have lowercase letters just like we do? But see, this here can be written like this. We could do that if you wanted, but I want to do other stuff. But I think you can see that it kind of looks like they're reciprocals almost, doesn't it? They're not exactly reciprocals, but they're kind of like reciprocals. And just remember that this epsilon 0 is a more fundamental constant. There's only a handful. There's Planck's constant, the speed of light, the permittivity constant. There's one for magnetism called the permeability, dealing with magnetism. I'm forgetting a couple, but there's only a handful of what they call fundamental constants. And as far as we know, these fundamental constants apply everywhere in the solar system and in the galaxy, or even in other galaxies. Isn't that interesting? Okay, well, great. So we talked about that. Well, do you have any comments or questions before we'll try working some problems?
I just I want to let you know, it says that your bandwidth is low, so you've been very the video's been very choppy.
Oh, my video is choppy.
Yeah, and it's a little hard to see the board. I don't know how it is for the others, but it's almost like it's just right out of focus, and so it's kind of hard to see everything.
Uh-oh, it's out of focus.
Yeah, that's pretty much the same I'm getting.
I don't like the sound of that at all. Well, maybe if I moved it a little closer, I don't know if that's going to help any. I moved it a little closer. It's crystal clear on my my computer, but you guys say it's a little bit fuzzy?
A little bit.
I don't like the sound of that. Let me call my or mention that to my IT person. Okay, this will just take a minute.
It might be something as simple as the lighting too.
I might need more lighting in here.
Maybe, I don't know.
Well, I've got 3 lamps on, and there's no bulbs out. Maybe I need a stronger bulb. Well,
Oh, so it's almost like the camera just isn't picking up a high enough resolution.
yeah. Well, this is a plugged-in camera. What if I use the computer camera? Let me try that. I'm going to unplug this camera. And I'm going to try to use the the other camera. Maybe that was a big mistake. I hope not. That might have been a big mistake. I'm not getting anything now. Probably shouldn't have unplugged that.
You might have to restart your video once it tries to pick up from the other camera.
Okay. All right, well, we're going to restart it then. That's fine. And we're trying to restart the video now. And we're trying, we're going to use the built-in camera. We'll see what happens. They're complaining about the camera, and I unplugged it, and I'm trying to go back to the old camera, the built-in camera. Box in the corner. Am I looking in the corner of my room here? What are you talking about, box in the corner? Oh, yeah, I see that. Oh, okay. Let me do that. Hang on. Just hang on a minute. We got a bright idea here. Okay, and then we'll continue on with our fun here. Okay. Okay. I've done what my how do I turn my camera on? Oh, okay. Well, on the bottom, I don't see where it says turn the camera on. Well, right now I'm looking at a picture of, I think it's Jacob. Is that you, Jacob? No, it's one of my students. Yeah, I see that. Okay, I don't see myself yet. I pushed start video. I do not see myself. Hey, can you guys hear me?
Yeah, I can hear you.
Yeah, they can hear me. Now I need
Yeah,
to
I can
pin
see you.
myself, but I don't know how to pin myself. There's no picture of me on here. Well, all I have right now is Jacob Reed's name on my page here. And yeah, well, how do I do that? Hey, now wait a minute. Oh, there's another wonderful student. Uh-huh. Right-hand corner. What about it? I don't see any place that says pin myself. Maybe I should give up and put the old camera back on, huh? I think I goofed up. Okay. Okay, well, we're having a disaster now. We've got a lot of wonderful students all online here, and I think they can hear me. The first camera was better than what I had. Well, what I'm looking at right now is some of my students. Okay. How do I pin myself though? I don't see it here. Doesn't say pin me on the right-hand corner of my screen. Okay, now there. I think maybe I can pin myself now. I see my picture there, but it's not. There's 3 little dots. Should I click that?
Yes.
Hey, I just found myself again. I don't know if I pinned myself or not, but I see my stuff on the board here, but it's kind of fuzzy.
It's very
Okay, we're going to put the external camera back on. We're just a minute now. Just one tiny minute. Okay. I don't know if this is going to be any better for these students. Hey, students, is that any better?
It's about the same.
Yeah, it's better than the other camera though. Or
Yeah, way better.
yeah. This camera is way better.
The students say that it's better. Point it up just a tiny bit. Not much. How's that? How's that? Maybe we better go ahead. Oh, okay, just a minute. I'm going to wipe off the camera lens with my shirt. Okay. It's a foolproof plan. Going to wipe off the camera lens. There we go. Okay, I wiped off the camera lens with my shirt. I wonder if that helped any. It's more blurry now. Okay, well, we'll I'm not too crazy about trying to get this better. Just a minute.
Point your computer screen down just a little bit, not the camera itself, just the screen.
Well, how's that?
Yeah, it's as clear as it'll be. We'll have to fix it later.
No.
That's okay, isn't it the way it is?
This is actually an improvement.
I'm sorry, I didn't understand that.
You need to take me off speakerphone.
Okay, you're off speakerphone. Well, I'm going to continue this wonderful lecture, I think. Bye for now. Okay, we're going to work some problems now. Let me find us one here. And let me know if you guys can read that. Okay, well, we'll start with we'll start with a single. That thing's dead. Let's forget that one. Just a minute. Oh. Okay, we're going to start with a single charge. There we go. Let's say it's 5 microcoulombs. This is a Greek letter, micro. And we'll have another charge over here. We'll call this our test charge. We'll put our test charge over here. And we're going to find the force between them. Now, what does that look like to you, that distance there? Let me measure that. That looks to me like about in the ballpark of 20 centimeters. So it's 20 centimeters. And there's going to be a repulsive force on this test charge. I like my forces in red. And that force is going to equal KQ. Well, we don't know what the test charge is. Let's just make up something. Say it's 2 microcoulombs. 2 microcoulombs. You need this in meters, 0.2 meters squared. Now you know what K is. It's 8.99 times 10 to the 9th Newton meters squared per coulomb squared. And we're going to get the force of repulsion there. Now let me ask one of my students here after that disaster. Zach, unmuted. Tell me if you can read that. Can you read that, Zach?
No.
Was that a no?
Yeah, no.
Was that a yeah, no?
Yeah, I said no.
You can read it.
No, I can't read it.
No, you can't read it.
No. I see K5 smudge, 2 smudge over something. K equals 8.99 times 10 something.
K equals 8.99 times 10 to the 9th. You can't read that, Zach?
The 9th is gone. I think it is 4. Basically, when everything gets that size, it's too small.
Well, I didn't understand you. I'm sorry.
I was
Let me ask
saying,
somebody else here. There's something about my audio that isn't that great. Let's go to my friend John. John, can you read that?
Not really, sir. It's very hard to see, and don't even want to think about when it gets more complicated. Like I can see F and I can see K. I can see some of the numbers, but it's real. It is not clear.
It's not clear. What if I made it darker, John? What if I made all these numbers darker? Can you read them better now?
I would say that is helping quite a bit.
That helps a little bit.
Yeah.
Well, good. I'll just try to make everything as dark as I can. Now, what I want you guys to do is I want you to plug that stuff in on your calculators and tell me what that force is going to be, that red force. I'm going to do it. I want you to do it. And then I'll ask one of you what you got. Well, I got an answer. Let me ask somebody here. How about my friend Chastity? Chastity, did you plug that equation in
No,
your?
I didn't.
Yeah.
I can barely see it to even know what to plug into my calculator.
No, that's terrible. I guess I need a thicker pencil, maybe. I haven't figured out how we're going to solve this problem. Let me pick on somebody else here. Let's see. How about my friend Stephen? Stephen,
Yes.
can you read that?
Not exactly. I'm saying 5 microcoulomb times 2 microcoulomb over. I can't pick up if that is a 0.2.
0.2 meters.
I can't. 0.2 meters.
Yeah, that's
Okay,
an M there. That's a meter.
Okay, I can't see what that actually said. Okay.
Well, I don't know what we're going to do, guys. We're just going to have to tough it out, and until we kind of get used to each other. But that's a square there.
Right.
And I'm going to try to write real dark so that you guys can see this stuff. And I forget who I was just talking to, but I got an answer. I know what this answer is, and I want to see if some of you guys can do it. How about my friend Daniel? Daniel, did you figure out what this is equal to?
I think so. If everything I typed in was right from what I can make out, I'm getting something like 2.2475
That's what
times
I
10
got.
to the 12.
That's what I got. I got
Okay, good.
2. See, I'm going to write dark now. 2.2475 newtons. Because see, the units will cancel. The meter squared will cancel. The coulomb squareds will cancel. The micros don't have units. They're just 10 to the minus 6. And we just figured out the force between these two. And I hope some of the rest of you got that. If anybody else got that, I want you to say uh-huh or yes. Go ahead, I'm listening.
Did you get that to times 10 to the 12th?
No, this answer isn't to the 12th. It's just 2.2475 newtons. Now, who am I talking to?
Zach, I just typed in everything that I see, and I have 2.24 times 10 to the 12th.
Okay. Oh, I think I know the problem. Tell me your name again.
Zach?
Zach. Zach, this micro means 10 to the minus 6.
I got you.
And if you put 10 to the minus 6 in here, 10 to the minus 6 in there, you'll get my answer. You okay now?
Okay. So what's next to the 2 then? Is that just
What's next to this two?
that 2?
That's a Greek letter micro. Here, let me write it for you. It's a micro. It means 10 to the -6.
Okay.
You need to be familiar with all those.
Yeah, I didn't.
Milli.
That was 9 there.
You know what milli is. That's 10 to the -3. And mega, that's 10 to the 6th. See, I'm writing darker.
Yeah, I'm very clear.
You can read that now, right?
Yeah.
Good. Well, we're making a little progress. My theory is we just try to do the best we can. Now, about this test charge, there's something they call electric fields. You know there's gravitational fields. We live in a gravitational field. Well, they have electrical fields. And what an electrical field is, an electrical field is the electrical force divided by your test charge. See, that in this case, it was your test charge. Well, if you wanted the electrical field, you would have to divide this by the 2 microcoulombs. Let's do that. I'm going to find the electrical field here at this location. It would be this 2.2475 newtons divided by the test charge, which is 2 microcoulombs. Okay, we're going to get the electrical field. The electrical field is in newtons per coulomb. It's force per charge. It's a vector, actually. Put little vector symbols over them. Now I'm going to do that and see what I get. I got an answer. Now what I'm getting is a very large number. I'm getting 1.124 mega newtons per coulomb. My calculator actually says 10 to the 6th. See that micro is 10 to the -6, and it's in the denominator, so that gives you a very large number. That's the electric field, and here I'll show you what that electric field looks like. Well, it looks like this. That's the electric field. It's 1.124. If you want to go times 10 to the 6, that's fine with me. That would be newtons per coulomb. So I've told you what electric fields are. And I've told you how to find forces between charges. Do you have any questions so far? Well, okay. Now that's just having 2 charges there. Let's talk about forces and electric fields if you had 3 charges. I'm going to start over again now. I'm going to try to write darker. Okay, we're going to put a positive charge here. And we're going to come over here. And we'll put a positive charge there. And then we'll put, this is at a distance of, we'll say it's 0.8 meters. And we're going to come up here. And we'll put a negative charge there at 0.6 meters. Now what we're going to do is we're going to give these some values. How about our little friend, what do we have? 5 microcoulombs there. Was this 2 microcoulombs? I forget. I think it was. And we'll just say this is, we'll make something up, maybe 3 microcoulombs. There we go. Now I'm going to do a problem, but can you guys read that? Let me ask somebody here. How about my friend, trying to find one of these students I haven't called on. I don't know, Daniel, if I've called on you before. Daniel, can you read what I've got so far, Daniel?
Yeah, I can read all that.
Ah, wonderful, wonderful. Okay. Well, let's put some red stuff on here. Now we know that unlike charges attract, so there's going to be an attraction that negative and that positive, they're going to attract, so there's going to be an attraction, and you can see it there. But there's also going to be an attraction here. Now we need to find out exactly what those amounts are. And our goal is to find out what the electric field is. How are we doing on time? We're doing okay. We'll take a break here in a little while. But we've only been going an hour so far. And this is a 3-hour deal. We're gonna figure this out. Let me make a little room here. I might need that room. Okay, let's call this maybe, give it a name, call it F1. We'll call this F2. And we're going to find out what those are. Well, F1 is K, 3 microcoulombs, 2 microcoulombs, 0.6 meters squared. F2 is 3K, 3 microcoulombs, 5 microcoulombs. Now we need this distance between them. I don't know if you're familiar with 3, 4, 5 triangles, but the way they work is if this is 4 and this is 3, this is 5. It's called a 3, 4, 5 triangle. Only this is an 8, 6, 10. So this distance here is 1.0 meters. Did I lose anybody on that? If you don't know how I got that, you could go 0.6 squared plus 0.8 squared square root. And you know what you'll get? You should get 1.0. Somebody do that and see if I'm lying to you. Take that on
I
your
actually have a
calculator.
quick question.
Go ahead.
On the 2 equations for F1 and F2, is that
Yeah.
the same letter you have in front of like the 3 microcoulomb and the 2 microcoulomb? Like it looks like an H and a K. Are they both Ks?
That's a 3 microcoulombs.
Yeah, before that, like the constant that's before
Oh, that's a
it.
K. Yeah, that's Coulomb's constant.
Okay, it looked like an H on the video. I wanted to make sure.
Yeah, you'll get used to my writing. Remember, Coulomb's law goes like this. It's got a K and a Q and a Q and an R squared. And that K is called Coulomb's constant. And it's equal to 8. But thank you for asking. 8.99 times 10 to the 9th.
Gotcha.
Good. Now who was that?
That was Daniel.
Daniel. Thank you, Daniel. All right. Now, I don't want to forget this here. This is 1.0 meters squared. Now, I want you guys to do this for me. I'll be quiet for 1 minute, and I want to know what the value of F1 and F2 is. Get your calculators and see if you can do that. Well, I did that, and for F1, I got, well, wait a minute. For F2, I got 0.13485 newtons. And for F1, I got 0.14983 newtons. They're pretty similar. This is close to 15. That's close to 13 and a half. They're pretty similar, but F1's a little bigger. Let me make F2 a little smaller. See, it's a little smaller. There's F1 and there's F2. Now what we're going to do is we're going to add those. Because, see, they're really vectors. This is a vector. I don't know if you remember how to add vectors, but we're going to do it. But before we do, did anybody get those numbers? Did I get those right? How about my friend Stephen? Stephen, did you get these numbers when you plugged these in? Stephen's not answering me.
No, sorry, I forgot to unmute.
Well, that's
I'm still
okay.
trying to set up my calculator properly.
That's fine. I just love some feedback here. How about my friend Jacob? Jacob, did you get these numbers when you plugged those in? Jacob's not answering me either. Well, how about anybody? Huh? Did anybody get these numbers? Did I do those right? We got to make sure this is right.
I got the same numbers, but my decimal place was in a different spot, so my math was probably messed up. Like I got 1.498 for the first one.
Really?
What
Well, let me
number?
do mine again. I could be wrong.
What number's in the front? I can't see the number next to your finger. After the K, it's 3 on the top.
The K is 8.99.
After
Had the wrong mic selected.
E to the 9th times 3e to the minus 6 times 2e to the minus 6. Then you have to divide by 0.6. You have to square it. No, that's what I'm getting. I'm not getting 1.4 something. Do yours
Yeah.
again. Who was that I was just talking to?
That was Daniel. Like I
Yeah.
said, my math was probably wrong somewhere in there.
We'll do it again. Daniel,
All
did you put in a 0.6 squared?
right. Yes.
And you didn't get 0.149. Did you put in 3 times 10 to the minus 6?
Nope, that's what I missed. Yeah, I left out the -6. Never mind. I'm good now.
Don't leave it off. If it's a micro, it's a -6. How about this one? Anybody get that? 0.13 something. Anybody get that one? Nobody's answering me.
Still trying to figure out how to plug all this in.
Yeah, I'm gonna be honest, sir. I really have no clue what's going on right now.
How about, let's go to my friend Stephen. Stephen, did you get 0.13485?
I got the number.
I didn't hear Stephen. Stephen, did you get that 0.13485?
I only just now figured out how to input the scientific stuff.
Well, good for you.
I'm working on that now.
Well, that's good. We have to know how to do that. Well, what about my friend Zach? Zach, did you get 0.13485?
Right now, I just got this top answer finally.
I didn't hear Zach.
I just got the top answer, so I'm typing it in to see if the second one is working.
Boy, I'm having trouble hearing. I don't hear so good.
Yeah, I
Zach.
got my F1's the same as yours.
Now, who was that just talked to me?
Jacob.
Jacob, you got both of those numbers, Jacob?
I just got the top one the same.
Okay, well, get the other one. But see, we're going to have to add these now.
Yeah, I'm not getting the same bottom number at all. I got 0.05. Is it another
Not
3
getting
at the
0.13485. Well, let me do it again. Maybe I goofed up. I'm going to go 8.99 e to the 9th, that's k, times 3 e to the minus 6, times 5.
I had a 2 instead of a 5.
Yeah, I got both my numbers match. I got them.
That's what I get. I think I did it right. But see, we have to add those. Those are vectors, and do you know how to add vectors? Let me refresh your memory.
I did at one point.
I wonder if I have enough room down here. Maybe barely. Maybe barely. What we're going to do is we're going to take F1 and we're going to add it to F2. But they're vectors. These little symbols represent that they're vectors. So what you have to do is you have to take the components. Now the components, there's X and Y components. The X component on this F1 is 0, and the Y component is 0.1, well, it's negative 0.14983. And now we're going to add F2. Well, F2 is just a tad more complicated. What we need here is we need to get this angle. Now that angle, if you have a 3, 4, 5 triangle, and we do, well, it's really a 6, 8, 10 triangle, or a 0.6, 0.8, 1.0 triangle. That angle there is 36.87 degrees. I want you guys to memorize this triangle. Professors put these 3, 4, 5 triangles on exams all the time. I'm trying to draw a 3, 4, 5 triangle. And this angle here is 3687. And the reason I know that is because if you take the tangent of 3 over 4, that's the opposite over adjacent, you will get 0.75. And if you put 0.75 in your calculator and hit the arctangent button, you'll get 3687. I want you to memorize that. And so that angle is 3687. And now we can add F2 to this. I'll tell you what F2 is going to be. I'll write it like this. It's going to be 0.13485. Oh, wait a minute, it's a negative, isn't it? It's a negative 0.13485 cosine of 3687, comma, negative 0.13485 sine of 3687. So I'm going to get those amounts and I'm going to put them right in here, and we're going to add these up, and we're going to get our vector force. I just need a little room here is all. If you put this in your calculator with me, 0.13485 times the cosine of 3687, you will get minus 0.10788, comma, it's an 8, comma, 0.134855 times the sine of 3687, negative, it's negative 0.08091 maybe. And now we can add these up and get our resultant. When you add vectors, you get the resultant. Well, 0 plus this here gives you a minus 0.107. Let me just round it off because I'm running out of room here. But now when you add these, they're both negative. So here's what you get. You get a negative 0.2307. We have just got the resultant in components. Did that make a lick of sense to anybody? Probably not.
Bits and pieces.
So say that
The whole
again.
piece. Bits and pieces of it, yeah. The entirety of it, some of it's kind of confusing.
Well, not if you do it enough. Now we're going to get the resultant. Now to get the resultant, I need this room down here to write. Yeah, I need the room someplace to write. How about up here? To get the resultant, you're going to have to take the square root of the 0.1079 squared. It's really negative, but when you square it, we don't care whether it's negative or not. turns out to be plus. And the negative 0.2307 squared. This will give us the total force. Okay, I'm going to do that. I want you to do that too. I want to see if you can do that. I'm going to do it. Go for it. I'm getting 0.2547 newtons. 0.2547 newtons. And here I'll draw it for you. It's kind of down here. This is the resultant force when you add these two. See, when we add these two, we'll call it the resultant force. And we have it. It's I can tell you how far it goes over to the left. It goes over 0.1079 to the left and 0.2307. It's actually pointed down a little bit steeper, more like that. Yeah, it's more like that. Now, if you wanted to, that's the resultant force. If you wanted the electric field, you would have to take that force that's acting on that body. And remember what electric field is. Do we have room here? Barely. Electric field is force per test charge. Well, this you could call that your test charge. It's 3 microcoulombs. So it's going to be a large electric field. Here's what it will be. It will be 0.2547 newtons divided by 3 microcoulombs. And what I'm getting is 84.91 kilo newtons per coulomb. My calculator has it 84,908, but that's 84,000 newtons per coulomb. And that would be, the electric field is going down at that angle. You could even figure the angle if you wanted, because we know the components. The components are, where'd they go? Well, F2, there's a component, I erased F1 to make more room. Well, I've told you about electric fields now, and I've told you about Coulomb's law. We've talked about a single point charge. We've talked about 2-point charges. And on this problem here, we had 3-point charges. We're going to take a little 5-minute break, go use the bathroom, stretch a little bit. And we're going to come back, and if we're lucky, we're going to learn about charge distributions. So go take a 5-minute break, and we'll be back. Take a break. We'll be back. Well, 5 minutes is up. And what we're going to work now is a couple of problems, hopefully using the information that we've studied. Now, you do have some homework. Let me mention that. According to the course schedule, your homework is problem 549 on page 227. And 555 on page 228. And it's due August 21st. Now, today's the 18th. It's Tuesday. 19, 20, 20. That's Friday. These are due Friday at midnight. So you got plenty of time to do them. Now, when you do your homework, I wonder if anybody's listening to me. Let me see if I've got any students.
Yeah, we're
okay.
listening.
Good deal.
Yes.
When you do your homework, read the syllabus. It says, write out the problem on engineering paper. Get you some engineering paper. Graph paper will work. You can get some cheap graph paper at Walmart. I think I got a pad for 88 cents of just cheap graph paper. That'll be okay. Or you can use that expensive engineering paper. Write out the problem completely exactly as it is in your book, or in your e-book, I guess. And then draw the situation. Which, I'm going to do that in just a minute. Draw your diagram and label it. Draw it to scale. I'll try to do that. I'll try to draw mine to scale and see if you can use Coulomb's law and answer the questions. That's what you're going to do. And then submit it on Blackboard. There should be a link after you have done your problem. Some of my students have what they call a CAM scanner. I guess on their phone, sort of a combination phone and scanner. I don't have one.
Quick question as far as submitting the homework.
Yeah.
I have you for thermo as well, and we were talking about it earlier in your class.
Yeah.
And there wasn't a link up on your Blackboard for
Yeah.
thermodynamics.
Now tell me your name.
Daniel.
Daniel. I've contacted my IT person, and we're going to fix that.
Okay.
We got till Friday to get that fixed. We'll do
Yeah,
it.
no worries. I was just wondering if it was already up or.
Yeah, we'll get that figured out. So there's your homework. It's due Friday at midnight. But I'm not going to do your homework. I'm going to do a similar problem. Let me make some room here. And what I wanted to do was problem. Just a minute here. I had it right here. I'm going to do 553. I'm going to write big for you guys. 553. Maybe I can figure out how to get this where you can read it. That would be nice too. Okay, this says you have point charges 1 meter apart. So let me draw that. These are both, no, one's positive and one's negative. And this one is 25 microcoulombs. It's a negative, and this one's positive 50 microcoulombs, and they're 1 meter apart. Okay, they're 1 meter apart. What is the force on the third charge? 20 microcoulombs placed midway. Okay, well, we're going to put a third charge right here of, I'm doing problem 553 now. It's in your book or on your electric book, e-book, electronic book. And this one's halfway between. So that would make this, if that's 1 meter, that'd make that a half a meter, wouldn't it? From there to there, and this would be a half a meter. Okay, and this one is the 20 microcoulombs. It's a positive 20 microcoulombs. They want to know what the force is on that charge. Okay. Well, I'm going to get a red pencil or pen, red pen. And see, this is going to be attracted. This is positive, and it's going to be attracted. But this is going to be repelled. But you know what? It's going to have a repulsion twice as big, if that makes sense, because 50 is twice as big as 25, and we're going to have to add those up. Well, that'll be easy. Well, why don't we call this F1 and F2? That'd be good. We'll see if we can get the correct answer here. Okay, well, F1 is going to be K. Hope you can read my writing. That's not an H, it's a K. Times, if that's F1, it's times 20 microcoulombs times a, now don't get confused. I know it's a minus 25, but I'm just getting the amount. I know it's going to the right because it's repelling, and the distance, you have to square it. Okay, there you have it. Now we're going to get F2. Here goes. F2 is going to be K. Nice and dark where you can read it. Times the 20 microcoulombs times the 20. Wait a minute. That's times the 50 microcoulombs. But it's also 0.5 meters squared. Now I'm going to shut up for a minute, and I want you guys to do that. I want to find out if you guys can do this. So go ahead. I'll be quiet. I want these answers. All right, I'm going to call on one of my excellent students here.
In the formula for F1, should the 25 microcoulombs, does that need to be negative or should that be positive?
Well, you can put a negative in there, but what really matters, is that Daniel again?
Yes.
I think maybe I'm slowly learning some of your voices. F1 is going to the right. F2 is going to the right. Let's don't confuse ourselves by making it negative. That might make, you might start thinking, oh, it's going to the left, it's negative. Well, it's not going to the left. So don't pay any
Gotcha.
attention to that, Daniel.
Okay.
But thank you for asking. Well, let me go to Jacob. Jacob, do you have either one of these?
Like the four. I do not. I'm still plugging them in.
Well, go ahead and work on it. That's all right. You know, the tortoise and the hare story.
I might be a different kind of slow though.
No, you'll be fine. I'll pick on John. John, did you get either one of those?
Sir, I'm gonna be honest. I am just not. I'm not with the group. I'm not understanding what's going on.
Okay, John, that's what I'm here for. Do you have a calculator?
Yes, sir. Got one in front of me.
Can you put in 8.99 e to the 9th in your calculator? Can you do that, John?
Yeah, sure. You want it to the 9th power? Like times-
Yeah, to the 9th power. 8.99 e to the 9th power.
Got it.
Can you multiply by 20 e to the minus 6? You can do this, John. And then multiply that by 25 e to the minus 6.
I multiplied it by 25, and what do I need to do with minus 6?
Yeah, 25 e to the minus 6.
Oh,
And then I want you to divide, we're dividing by 0.5 squared. Can you do that? And tell me what you got.
okay. I'm dividing by, is that 0.5 squared?
Yeah, it's 0.5 squared. What'd you get?
I got 17.98.
Good, that's the answer. Good for you. See, you
Oh,
can
okay.
do this. We're not lost. It's
What does that mean?
17 point. Now my calculator says 17.98. Is that what you just said?
That's what I got, but I don't understand what that means. What did we just?
I tell you what it means. It's 17.98 newtons.
Okay, so we solved for a force. Okay.
Yeah, newtons is force. Now the reason why it's newtons is that this K has units of Newton meter squared per coulomb squared. I know that's a micro, but that doesn't have units. That has a coulomb, and that has a coulomb. And then when you divide by meter squared, can you see that the coulombs cancel? You got a coulomb times a coulomb, you're dividing by a coulomb squared, they all cancel. And the meter squareds cancel. And so you're left with a Newton. That's how come the answer is in newtons. Now let me pick on another wonderful student. Chastity, we're going to pick on you.
I got 35.96 on the bottom.
Hey, that's what I got. Good going. I got the 35.96 newtons for F2. Now, we have to add these together to get the answer. Because see, the total, you understand? It's like you're tied by two ropes and two people are pulling you on those ropes. Well, the total, you have to add them up. Okay, I'm going to add those up. Here goes.
All my answers, my decimal place is 1 to the left.
You're getting one decimal place to the left.
Yes, sir.
Now, who am I talking to?
Jacob.
Jacob. Which one you want to do? This bottom one, Jacob?
Either one.
Okay. Well, on this bottom one, Jacob, take 8.99 e to the 9th. Did you do that?
No, I went by 10 to the 7th.
Oh, it's e to the 9th. That's why you didn't get it.
It's e to the 9th for k.
Yeah.
Times 10 to the 7th.
Yeah. K. Here, let me write it again. K is 8.99 times 10 to the 9th, not 7. And you'll get good answers if you use the right numbers. Jacob,
Okay. I was the screen blurred.
you
I
feel
thought
better?
No, yeah, I thought the 9 was a 7 because of the. All good.
Oh, is my stinking handwriting gonna cause problems? Does my 9 look like a 7?
No, it's just the screen on the earlier board. You're good.
Yeah, we're gonna do the best we know how here. Okay, now I'm gonna add these two up. Here goes. I'm adding them up now. I'm getting a total of 53.94 newtons, and it's going to the right. Now that should be the answer in the back of the book. Let's go to the back of the book and see how we did. There's answers back here someplace. This is chapter 5. This is problem 53. And we're going to see what they said. Now they're right about 99% of the time, but they're not always right. They make mistakes just like you and I do. But here's what they said. They said the answer is 53.94 newtons. That's what the answer book says. Now let's compare that with our answer. Hey, look at there. We got 53.94. And that's what the answer book says, 53.94. I feel good. I have that warm, fuzzy feeling of accomplishment. Do I need to explain anything else about that problem 553, or can we go on? If nobody says anything, I guess you must understand it.
So what did we solve there?
We solved.
Found.
There's a charge here in the middle. They put a charge right here in the middle. And we solved for the force on that charge. Now who am I speaking to?
Oh, it's John Gilliam.
John,
we
solved for the force on that charge that they put in between these two charges.
Okay, is that
the total force? You understand? It's the total force.
Okay, is that how we should think about it also? Is it like, is the charge a force that exists in between these two particles, or is it like kind of like almost like a cable kind of from holding them together, or how do you think about that?
Well, it's a little bit like the Earth and the Moon, okay? You got the Earth, you got the Moon, and let's say you have a rocket that's halfway between the Earth and the Moon. What is the total force on the rocket? Well, you can't use Coulomb's law because you'd have to use Newton's gravitational law, but the Earth attracts the rocket and the Moon attracts the rocket, and you're going to have to add the two up. In that problem, though, they're opposing. That's all we're doing. We're finding the total force on a positive charge halfway between these two charges.
Okay. Okay. But for like other problems down the line, it sounds to me like what you're saying is the charge can change depending on your relation.
Yeah, the charge can change. You could put a different charge in there. Absolutely.
Okay.
And you could put, I'm sorry, I forgot who I'm talking to again.
Oh, it's okay. I'm John.
John, okay. John, we could make this more interesting. We could put the charge over here someplace. Or we could put it over here. Hey, we could put it anywhere we wanted. We could have it down in here someplace or up in here. Okay, well, great. Well, let's do another problem. That wasn't too terribly bad. Go ahead, I'm listening.
Sorry to bring this back up, but my decimals are still off to the left.
I'm having trouble with my audio. Say that again, please.
My decimals are still off to the left.
Okay, well, maybe I should write it out carefully. Here, let me write the numbers for you. Now, is that John again?
No, it's Jacob.
Jacob. Okay, Jacob. I'm writing these numbers down now. All right. Is it 9.98? Is that what we've been using?
For what? K?
For your K.
8.99.
Yeah, I had a senior moment there.
All good.
Thanks for your help. It's 8. I hope you can read my writing, Jacob. It's 8.99.
Times 10 to the 9th times 50
Yeah,
times 10 to
50,
the
10 to
negative
the minus
6
6.
times
20
20
times 10 to
times
the
10 to
minus
the negative
6.
6.
And then see, you have to divide by 0.5
Times-
squared.
Uh,
Do that on your calculator. You should get, I think it's 30, you should get 35.96. Do you? I'm gonna
Yes,
do
sir.
it.
That fixed my issue.
Say that again.
Yes, sir. That fixed my issue.
Yeah, good, excellent. Okay, all right, next. Now, the next problem we're gonna do is 555. So let me make some room here. 555. We are going to do problem 555. Now let me find it. Okay. Now they've got two silk threads there and an angle of 5 degrees. I'm going to need my protractor to do this. See, when you do your problems for me, I want you to measure the angles. I want you to measure the distances. They said there's a 5-degree angle here. Okay, well, I'm going to make a 5-degree angle. Here it goes. You'll need to buy a protractor, and I'm going to measure 5 degrees. Okay. Well, you know, 5 degrees isn't very big. I'm sorry, but it's pretty dang small. And here I won't measure this one. I'll just draw it pretty much the same. But I've tried the best I know how to make that 5 degrees. Let me make them a little longer. But see, I measured those. I actually measured the angles. Get yourself a ruler and a protractor. Okay, now this angle right here is 5 degrees. I'm reading this problem now. It's problem 550. It's 555. Hope you can read my writing. 555. All right. Got lost there for a minute. Now, each of these has a mass of 5 grams. You can write it out if you want. And the strings are 50 centimeters long. Now, I don't know if I did that to 50 centimeters. 50 centimeters, nah, that's only about 25 centimeters. So they're really twice that long, but hey, I can scale this thing any way I want. Okay, I got lost. Let me keep reading here. The balls are given the same charge. The threads hang 5 degrees. Find the magnitude of the Q. Find the signs of the 2 charges. Well, can you tell they're being repelled? They're repelling. So that means they're both the same charge. They're either both positive or they could both be negative. We don't know. Let's just call them both positive, okay? But we don't know what the charges are. We'll just call it Q. That'll be fine. Now we're going to take our red pencil and we're going to put the forces on these charges. Now, see this string here? The string is pulling on that charge with a force. I'll call it T for tension, all right? There's tension in that string. Just like on a guitar string, it's got tension on it. You go plonk, 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 it's under tension. Now, there's going to be a weight here. Let's call this weight W. And there will be a third force, and that's this Coulomb force. It's very small. Why don't we call that F? So we've labeled our 3 forces acting on our little mass there. And of course, you'd have the same forces here. It's just that the F is going this way and the tension's going like that. and the weight is coming down. The amounts are the same. Okay, now let's get this weight. Now, weight is equal to mg. I bet you've done that before in Physics 1. But see, this needs to be in kilograms. So that's 0.0005 kilograms. Gravity is 9.81. Now I want to see if you can multiply those two numbers. Go ahead. I'm going to do it. I want you to do it. We're going to find the weight. Well, I got an answer. I got an answer of 4.903 times 10 to the minus third. No, 905. Now let me go to one of my excellent students here. Let me pick on Stephen again. Stephen, did you get 4.905 times 10 to the minus third?
Yes, I did.
Yay, yay, good, excellent.
Good job, Steven.
Did somebody else say something?
Yeah, just a quick question. If you're converting from 5 grams to kilograms, isn't that 5 divided by 1,000? I think there's an extra zero.
Did I do that wrong? Let's see. Now, who am I talking to?
It's John. Sorry, it's John.
John. Thank you, John. Now 5 grams. The way to convert that is a kilogram is 1,000 grams. So if you take 5, divide it by 1,000.
Yeah, I think you're going to get 0.005 instead.
I did it wrong.
Yep.
John, you're absolutely right.
Hey, it's my Chem 1 skills, okay? That's a lot.
I'm proud of you. We're going to put a nice big thank you point up there. That's a thank you point for John for helping our class, because I did it wrong. So if you do this, what will that make this a -2, John? What do you think? Let me do it. Yeah, I think that's right. Now I don't have a minus here. That's an equal sign. Don't get confused. But thanks to John, we're off and running. We've got the right weight now. See, I'm quite capable of following up here, but with your help, we can do any of these. Now, here's what we're going to do. We're going to find this tension. Now, see, there's an angle here of 5 degrees. It's kind of hard for me to draw. Let me draw it separate here. You've got that tension there. And there's your tension. We want to find that. But there's got to be a force going up of 4.905. 4.905 times 10 to the -2 newtons. And see, the way you would do that is you would say that 4.905 is equal to the tension times the cosine of 5 degrees. See, you have a triangle here. And this is the adjacent side. Are you all familiar with SOHCAHTOA?
Oh yeah.
Yes, sir.
Now somebody just said yes, sir. Who was that?
Jacob.
Jacob, explain to the class the meaning of SOHCAHTOA. Go for it, Jacob.
It's just a mnemonic device to remember the relationships between
Jacob,
trig
say
functions and their
sine
triangle.
is opposite to the hypotenuse, and go for it.
Sine, opposite hypotenuse. Cosine, adjacent hypotenuse. Tan, opposite over adjacent.
That's it. SOHCAHTOA. And in this case here, the cosine of 5 degrees is equal to the adjacent, which is 4.905 over the hypotenuse. Now you can do a little algebra and you'll find that the did I do that right? Cosine of 5 degrees is the adjacent over the wait a minute, I'm getting confused now. Just a minute. The cosine of 5 degrees is the adjacent over the hypotenuse. So this is wrong. No, it's right. It's right because see, if you multiply by t, you'll have t cosine of 5 degrees is equal to 4.905 10 to the minus 2. That's what I wrote. T cosine of 5 is equal to that. So now we can find our tension. Here goes. We're going to find our tension now. Well, you have to divide by the 5 degrees. Let me do that. If you solve this, you have to divide by the 5 degrees. Did you get the tension is equal to 0.04924 newtons? I hope you can read my writing. So now we have the tension. I'm hoping you're all with me. If you're not, just ask a question. Now what we're going to do is we're going to find this force here. So see, that's the electric force. And I'll tell you what it's equal to. It's equal to K, our little friend K, Coulomb's constant, times Q, well, they're both the same, divided by this distance between them. Well, I don't know what that distance is. You have to square it. I don't know what that distance is, but we're going to figure it out. And see, this is equal to, that's equal to T sine of 5 degrees. You see this value of T right here? We figured it out. It's 0.0492. And this little distance here, that's T sine of 5 degrees. If you want that, and what that is, that's the electric force. Now here's our equation. If we could only find this distance between these charges, we could solve for these Q's because they're both the same. We know what K is. In my classes, if I circle something, that means I know what it is. K is 8.99 times 10 to the 9th. We know that. T, we know that. We figured it out. It's right here. It's 0.0492 something. Well, how are we going to get this distance between them? Well, that distance between them, is this showing up? Yeah, there we go. It's equal to 50 centimeters. We're going to go 0.5 meters times the sine of 5 degrees. But that'll only give you half of it. That'll just give you that distance there. We got to multiply by 2. Multiply that by 2, and you'll get the total distance between them. Well, a half times 2 is just 1. It's just equal to the sine of 5 degrees. Okay, let me do that. The sine of 5 degrees. This distance D is 0.0875 blah, blah, blah meters. Not very long. See, if that's 50 centimeters, this is 8 centimeters. Well, closer to 9. Well, that is, no, the total is closer to 9. This distance here is about, what, 4.5 or something like that centimeters. But look at here, now we know what D is. And what we're going to do is we're going to solve for this force between, I think that's what they wanted. Read it, 555. It says here, oh, no. They want to know what the charge is. Look, we know what the tension is. We know what D is. We know what K is. All we got to do is solve for the Q. I could write that out for you. So let me write it out better for you. Here goes. And then I want to see if you guys can do it. Okay. Here we go. 8.99 10 to the 9th Q squared over 0.0871 blah, blah, blah squared equals, oh gee, I erased what the tension was. Somebody that's been taking notes, what was the tension? I erased it.
.0.04924 newtons.
0.049.
I wrote a 9. I don't know if that's what it was.
Yeah, it was a 9.
0.049.
24 newton.
246.
No, just 0.04924.
Okay, I bet that's right. Let me now. Who just told me that? Who is that?
Jacob.
Jacob. Now, Jacob, not that I don't trust you, Jacob, but I'm going to check it. I'm going to check it because
Please do.
Because I know that the t times the cosine of 5 is equal to this 4.9 stuff. So you take the 4.9 e to the minus 2 and divide by, I think you divide by the cosine of 5 degrees. 0.04924. 0.04924. By Jove.
Yes, sir.
That's looking pretty good. Okay, now guys, we're going to solve this equation. Here's an algebra equation. We only have one unknown. That's the Q. I want you to put all this in your calculator. No, wait a minute. Auga, I'm forgetting something. Aren't I forgetting sine of 5 degrees right here? See, KQ times Q, KQ times Q, divided by D squared equals the tension times sine of 5. Okay. Now you're going to put this in your calculator and you're going to find Q. I'll shut up for a minute. Go for it. See if you can do it. And then I'm going to call on you guys. I want to feel good about this now. Well, I got an answer. I'm going to peek and see if it's the answer in the back of the book.
I don't know how worthwhile it is for you to know this, but whenever you step out of frame, the camera focuses on the board and it's a lot easier to see.
Oh, is it focusing on me?
It might.
Oh, that's an interesting idea. Thank you for mentioning. Is that Jacob again?
Yeah, but John brought it to my attention.
Good going, John. In other words, if I get in here, then it screws things up.
I don't know. I just happened to notice when you were out of the frame, the camera refocused on the board, and it was like, it was
Oh,
very.
okay. Well, that's fascinating. Maybe it has some sort of automatic focus there. I'll mention that to my IT person. Now I'm going to look up this answer now. I got an answer, but I don't know if it's their answer. Let me see what they said. And this was problem 555. I'm not getting what they got. Let me tell you the stuff they got. They said that the tension, this is the answer in the back of the book. They said the tension is 0.049. Well, that's what we got. We agree with them on that. And they said the D is 0.088. Well, that's pretty dang close. What do you say? I think we did all right. It's a little different than ours. I think ours is good, but let me double check it. Well, I'm getting more of a point. Let me do this again. 0.5 times the sine of 5 times 2. I'm getting 0.087. They're getting 0.088. I honestly think they're a little bit off. So I'm a little bit unhappy with their value of D here. I think our value is better than theirs. And here's their value of Q in the back of the book. I hate it when we disagree with the book, because it makes you wonder, well, did we do it right? They said 6.1 times 10 to the minus 8. Now what did we say the answer was? Well, I don't know. I lost it. Let me do mine again.
Professor, are you there? Can I ask just a question or two?
Yeah, please do.
Okay, I understand all the trig we used. I'm just confused about a few things. When we solved for the tension, that was on the string from the ceiling to each ball, right? So that's
Yes.
that's at 5 degrees.
Yes.
And then you have, I guess I'm confused then, because I understand we use trig to find D, and then we had to multiply it by 2 because
Yes.
there's both those lengths. But what is the Q? Like what did
The
we
Q is the charge. It's an unknown charge. Remember, I think we use little q in some of our other problems. This one here, I'm using a big Q. I'm sorry to confuse you. It's just the charge.
Okay.
You okay now?
Yeah, and so that is the force that is keeping the two balls that D distance.
Yeah, now the Q isn't a force. The Q is the charge. But if these are both positive charges, they are pushing apart each other, right?
Yes.
Yeah, there's a force. And that force is equal to Coulomb's law, KQ times Q over D squared.
Okay. And so we can you're calling it Q squared over there because we don't know what the charges are, but we know that they're the same charge, whatever.
Yes. Very good.
All right, I'm with you a lot more.
Yay, good deal. And now let me do this again and see what I get here. Just a minute. I kind of got lost. Well, I'm not getting that answer at all. Let me try it again. I must have done something wrong. We agree with the T that the book got. Okay, here's what I'm getting, guys. When I solve for Q in this equation, I'm getting 6.02 times 10 to the minus 8 coulombs. Now the answer book, they got 6.1 times 10 to the minus 8. I'd have to see what they did. It's possible they used 9.8. Sometimes books use that for gravity, and we use 9.81. That could throw us off just a tad, but those are pretty dang close answers, aren't they? 602, 10 to the minus 8, 6.1, 10 to the minus 8.
We are
I think we
solving.
did okay on that.
Right?
Were you able to get that? Were you able to get 602 times 10 to the minus 8?
500 range. That's what I'm asking. Are we trying to solve this equation for Q?
Are we trying to solve for the, say that again?
Are we trying to solve this equation for Q?
Yes, exactly. I wonder if there's any way I could
I'm getting
get a
like
higher volume. How do you turn up the volume on this dang thing? I don't know how. I wish I did. Because I can barely hear you guys. But yes, who was that just asked me that?
Zach,
Zach. Zach, there's only one unknown in this equation, Zach. It's the
Yeah, and
Q.
I'm getting 540. I don't know why.
Say that again, please.
I'm getting 540.
Okay, well, let me do it again. Here goes. I'm going to take this number and I'm going to square it, Zach. Here goes. 0.087156. And I'm going to square it. Did you square it?
Uh-huh.
Now I'm going to multiply by this number. I'm going to multiply by 0.04924. And then I'm going to multiply by the sine of 5 degrees. Now make sure you're in degrees and not radians, Zach. You know what I'm talking about on your calculator?
Yep, I just checked that too, and it was good.
If it's in radians, you're going to get a goofy answer. Now I'm going to divide by 8.99, divide by 8.99, e to the 9th. Now I'm going to take the square root. Square root, I get 6.02 times 10 to the minus 8. Now you do it. And tell me what happens. How about anybody else that has trouble?
I was just wondering, why did you set the equation equal to t sine 5 degrees?
Oh, thank you for asking. That's an excellent question. Let's see if I can answer it. I just need a little room to try to explain over here.
All right, so I have a 6.02 times 10 to the negative 8th.
That's it.
Okay.
You're doing it. Now, who is it that's asking me about the multiplying by the
Jacob.
5 degree sine? Who is that?
Jacob asked.
Jacob. Okay, Jacob. Look at this charge right here. There's your charge.
Yes.
We know we have a weight coming down of 4.905 times 10 to the minus 2 newtons. We know there's a tension coming up like this. And we know that the component, see that tension has two components. This component is called T cosine of 5 degrees. And this little component is called T sine of 5 degrees. And then we have a third force that's your electric force. Let me put the actual forces in red. There's your gravity. There's your tension. And there is your electric force. And I'm talking to Jacob now.
Yes, sir.
Now, Jacob, the forces going up have to equal the forces going down. You got 4.905 something going down, and going up you have T cosine 5. They have to equal each other because it's just hanging there. The forces going up and down have to be equal. Now the forces going sideways, this here is T sine of 5. That has to equal this electric force. See, Jacob asked me, how come this electric force, which is equal to Q over R squared, is equal to T sine of 5 degrees. Well, the reason is the forces going to the right have to equal the forces going to the left. If it's going to hang there. Now, the reason why this is sine and cosine, that has to do with trig. I can go back over that if you want me to, Jacob. But I'm trying to explain how come. See, they have to balance.
Right.
Did that make sense this time?
Yes.
Excellent. Okay.
Can I ask a follow-up question to what Jacob, what you did there?
Yeah.
So I understand that we're basically balancing the forces because this is a static system. And
Yes.
you can write what you wrote. My question is, okay, so that T sine of 5 degrees,
Yes.
does that represent from one of the balls to the midpoint, or does that represent like the entire? So it's just, you know how we split this into two triangles, and we solve for the opposite side, and that's multiplied that by 2 to get the.
Now, who am I talking to?
Oh, this is John.
John. John is asking me, what does this T sine of 5 degrees represent? I heard you say that. What it represents is the pull horizontally of the tension. See, if you had somebody pulling on you with a rope, John, that rope is mostly pulling straight up. You can see that. But it's got a little bit pulling you over to the left. Now, the amount that it pulls to the left is T sine of 5 degrees, according to trigonometry. Did that make sense?
Yes.
Well, that's what that is. That represents
Yep.
the force in the horizontal. They call it the component. See, forces have components. The component going up of the tension is T cosine of 5 because of trigonometry. I'll explain that if you don't understand. It has to do with SOHCAHTOA.
No, I'm with you. We're breaking it the force into y and x. Forces.
Exactly.
What you're doing.
Well, I think we did the problem, and I think we did a good job. We got a slightly different answer than they did. We got 602 and they got 6.1, but we'll forgive them. I think they might have used a different value for gravity, but I'm pretty happy with it. Well, we have 10 more minutes, and you paid your tuition, I hope. And let me tell you about where we're headed. We'll meet every Tuesday night for 3 hours. We have another night on chapter 5, I believe, according to the syllabus. Let me check on that. I believe we do. It says here, yeah, we got another night on chapter 5. And then the following Tuesday will be chapter 6. But here's where we're headed. Unless somebody has another comment or question, I'm going to tell you where we're going. I'm going to erase this if you're happy. I'm going to erase it. You've been warned. Okay, we'll say goodbye to problem 555. Now here's where we're headed. We've talked about a single charge, 2 charges, 3 charges. We talked about, we had 3 charges, I think, on one problem. And on that one, we had 2 charges hanging from strings. But where we're headed is charge distributions. Come on now. And they occur in several different forms. They have lines of charges. You could have like a rod, maybe. I don't know. Take a comb and run it through your hair. It'll get all charged up. And so just pretend like it's got a bunch of pluses on it. Now I forget if you take a comb and run it through your hair, whether they're pluses or minuses. Let me just, do we have time to look that up? Not much, but let me look that up for you. I'm kind of curious. And let's see here. Does it tell you about yeah. There's a comb with on page 185, but they don't tell you which charges they are. I used to know, but I forget. But you can actually scrape charges off with your with a comb. Does it tell you which is which? I can't find it. But you can have a line of charge. I do know that, and we're going to study that. Like a charged rod, for instance. You could take a charged rod. Now, it has to be an insulating rod. You can see a comb is made out of what, plastic or rubber, and the charges can't travel. If you have a steel comb, you can't charge it up because the charges here. Let me show you what I mean. Here's a steel comb. Okay, I think I've seen steel combs. If you charge that up, the minute you put your hand on it, the charges will all repel each other and leave. If there's a bunch of pluses on here, they repel each other. And if you put your hand on it, they'll just go down your hand to the ground and they're gone. But if you have like a rubber or plastic comb, they can't travel. See, because that rubber's an insulator. The charges can't move. But we're going to do rods, charged rods. We're going to do rings. That'll be next time. You guys can read about it. If you have a ring of charge, okay? What we're going to do is we're going to charge up a ring. Now you can charge it negative, but I charged it up positive. You could have a charged ring. You could have a sheet or a plane. I don't know, like a big square flat plane of charge. You could charge it up, okay? Needs to be an insulator because, again, if it was a conductor, all those charges would go whoosh and try to get to the outside away from each other. They'd repel. But we could have or a disc. You see, this is a solid. See, that's a ring. It's empty in the middle, but a disc is solid, kind of like a metal plate. Okay, and you can charge it up. Again, it needs to be an insulator. I don't know what to call these, plates or discs of charge. And we're going to study those. Rods, rings, discs, or plates. Spheres. We'll talk about spheres. How do you spell spheres? I think it's SPH Did I spell spheres right? S-P-H-E-R-E? Come on, you guys. Is that how you spell sphere? I think it is. Now, if it's a conducting sphere, if it's a solid sphere, all the charges will repel each other and they'll be on the outside. There won't be any charges inside a sphere. If it's a hollow sphere, like a basketball, maybe. If it's a hollow sphere, and if it was a conductor, you'd still have the charges would all be on the outside. There won't be any charge. Well, it's hollow. There's no charges on the inside. They're all on the outside. So we're going to do spheres, discs, plates, and rings next time. And we're going to come up with the equations for each one. I've got 3 minutes left. When you do lines of charge, they use a symbol lambda. It's a Greek letter lambda. And what that is charges per meter, or I'm sorry, coulombs per meter. And when they do discs or plates, they use a Greek letter sigma. And what that is coulombs per square meter. They have names for these. These are called charge densities. These are charge densities. Charge densities. And they also have a rho. This is a Greek letter. See, that's a Greek letter sigma, lowercase. This is a Greek letter rho. And what that is coulombs per cubic meter. Now, you could have an insulating sphere. You couldn't do this with a conducting sphere, but if you had an insulating sphere, that looks more like an egg than a sphere. But we tried. You could distribute charges throughout this spherical volume. You understand you'll have charges inside, outside, everywhere. I liken it to if you cook some oatmeal and these charges were like raisins. Dump a box of raisins in the oatmeal, stir it up good, cook it, let it cool off, and then make you a big spherical glob of oatmeal, and it's got raisins distributed throughout the oatmeal. And that row represents the amount of charge per cubic meter. We'll need to know about these charge densities next Tuesday. Well, we've had a fun time. I hope you learned something. Read your book, do your homework, and I will see you in lab. I told you the lab number. It's in the northwest corner of the Northeast campus. I'll see you there on Thursday night at 5:30. I'll try to get there early and set things up. Did you have any last comments or questions? Because I'm going to close this wonderful time together out now.
What was rho?
Rho it's actually called the volume charge density. It's the amount of charge per volume. It's the coulombs per cubic meter.
All right.
Anything else from anybody?
Nope.
Well, we're going to do the best we know how, everyone. I enjoyed being with you, and we'll get to know each other personally. Hey, that'll be great. On Thursday, I'll get to know your faces and your voices better. Unless there's another comment, I'm going to go bye-bye. 5,
Thanks, sir.
4. Go ahead.
Bye-bye.
Somebody said something. Were you just saying goodbye? Okay, I'm going to sign off. 5, 4, 3, 2, 1. Goodbye. See you later.